Hi everyone. In the last video, we were still into introduction to reinforcement learning. So once we finish that section, I plan to move on to torch.rl and then into advanced reinforcement learning algorithms. But for today, we are going to take a look at torch.flatten. This function is most often used after convolutional layers and before fully connected layers in neural networks. So once your CNN extracts features from an image, you flatten them into a vector before feeding them into, let's say, a linear classifier. Okay, so this is the function, and this is the these are the default parameters. So the example that I'm going to be working with is this. This is X, and it's a 3 by 2 by 2. Okay, but before we start, it's important to know how PyTorch indexes dimensions. By the way, you can imagine this tensor, our X, as 3 images of dimension 2 by 2. So in terms of indexing, counting dimensions always starts from left at 0. So for this tensor with shape 3 by 2 by 2, dimension 0 is 3, dimension 1 is 2, dimension 2 is 2, and dimension -1, the last dimension, is 2. Okay, so when we look at this module, when we say, for example, okay, these are the default parameters, but let's say this was 1. When we say start dimension 1, it means when you flatten, keep everything before dimension 1, 2 in this case, and then flatten from dimension 1 onwards. So I will end up flattening this 2 by 2 section. And when you flatten a tensor, the size of the new dimension is always the product of the dimensions that were flattened. So when you flatten a 2 by 2, the result is going to have a tensor that has a dimension of 2 times 2, which is 4. Okay, and in terms of the enddim and dimension, when we say enddim is negative 1, for example, the last dimension, it means flatten everything up to and including the final dimension. But let's take a look at some examples. This is the first case. Okay, this is the first case. Here we are using the default parameters, and y is torch.flatten x, and this is the result, and this is the dimension of the result. Okay, so here we have this x, which is like 3 images of 2 by 2. You can think of it that way. So with no argument, PyTorch will use these default parameters. So PyTorch flattens from dimension 0, okay, all the way to dimension -1. So this 3 by 2 by 2 will become a tensor like this of dimension 12. So you can imagine this result as taking 3 small 2 by 2 images and unrolling every pixel into one single row of 12 values. So that's why we have this 12. Okay, let's look at a second example. So now we take y is torch.flatten this x, and this start dimension is 1 instead of 0. And you end up with this, and the dimension is this. So here the end dimension is, the start dimension is 1. So we keep dimension 1, I mean the first one, because we start here, which is that we keep the batch dimension. And then we flatten everything starting from dimension 1 onwards. So the 2 by 2 of each image becomes like just a list of 4 items. So the 3 by 2 by 2 becomes 3 by 4. You can imagine this as still having 3 images But now each image is a 1D row of 4 pixels instead of 2 by 2 grid. Okay. Now let's take a look at this example, the third case. Now y is torch.flatten x, and the n dimension is 1, which is this, right? We start from 0, 1, the n dimension is this, so we flatten only this section. This dimension will not change. So the 3 by 2 by 2 becomes 6 by 2. Again, don't forget that when we flatten a tensor, the size of the new dimension is always the product of the dimensions that were flattened. So you can imagine this as like stacking 3 images on top of each other vertically. So instead of 3 separate 2 by 2 images, you now have a more like a taller image of height 6 and width of 2. Notice that the batch dimension is gone. So everything has been merged into one structure. Okay. Now let's look at a more realistic case, the real world case. Now let's say x is actually, forget about this, maybe you can actually remove it. X is a tensor of dimension 5 by 1 by 28 by 28, and we use y is such that flatten this x, and the start dimension is 1, and y is the dimension of the resulting the result of this operation. So x here is a 5 by 1 by 28 by 28. 5 is the batch size typically, 1 is the channel, this is the height, and this is the width. So we have like a batch of 5 grayscale images. It is grayscale because the channel dimension is 1. If it were, let's say, 3, and that will represent RGB images. By the way, this is exactly the format of the MNIST dataset. So here, typically in such real-world cases, we set start dimension to be 1 because we always want to keep the batch dimension. So flattening start from 0, 1 here, and we keep the batch dimension intact while flattening the rest. So with the start dimension 1, we keep the batch of 5 and flatten the channel, the height, and the width. So the 5 by 1 by 28 by 28 becomes 5 by 784. You can imagine this as still having 5 images, but now each image is stretched out into a, let's say, a long 1D vector of 784 pixels. And this is exactly what you feed into a fully connected layer after a CNN. Okay. And this is it. Thank you for watching. Let me know if you have any question in the comments. Bye bye.